prime of c. For a function f and a number c, find f and c. The limit represents f prime of c. So essentially, if this is what you're looking at, and by the way, you can also, I know this change of x is like a weird thing. The limit as h approaches 0, -2 plus h cubed plus 8 all over h, if you want, if that's helpful for you. So if this is what we get after we plug into some function, what do you think the function was? What was the function? I'm assuming this is where the f of x plus h comes from. Minus f of x all over h. So the question is, what is the function? What is the f of x function? Do you think, Aiden? X cubed. So he's thinking, okay, the f of x function must be x cubed. And the location at which we are looking for the slope is what x value? Would -2. Now, Aiden, could you put into words how you knew that? Right, so he's thinking this is where he sees x plus h. So he knows that x was -2, right? Subtracting a -8 would become the +8. And before that, he knew that the whole function, the x, was just cubed because this x plus h that he plugged in, or would have had to have plugged in, is getting cubed. So your f of x plus h is here, minus your f of x all over h. It's clearly easier to see forward. So if I told you to find the slope of this, if I told you to find f prime of 2, you guys would do f prime of x probably first as h approaches 0. And if you knew that this was the function, f prime of x would be the limit as h approaches 0 of f of x plus h, would create that x plus h cubed, minus f of x would be subtracting x cubed all over your h value. And since we're actually looking for f prime of -2, he thinks, that's just me taking what I just wrote and plugging in a -2 for the x. -2 plus h cubed minus -2 cubed all over h. And here's where he's talking about that double negative turns to a +8. So much easier to see working forwards if you know the function and you know the location at which you're looking for the slope. But this is pretty much asking us to kind of think backwards. If this is your f of x plus h, what must your f of x have been? And also in there, knowing what the x substitution was as well. So your function is x cubed and your c value was -2. Does that make sense? There was a multiple choice a while back where we kind of, this isn't the first time we've addressed this issue, and it's never going to be easy to kind of look backwards, but you should be able to look at this type of expression, which is the definition of some derivative, and you should be able to think backwards, what was the original function? And sometimes that's all you have to do. This particular one was, what was the original function, and at what value is this attempting to find the slope? And that was at -2. Okie doke. Another type of equation or of problem that's just going to sort of make you think a little bit is to create a function, an image of a function that has these characteristics. And again, we've done this a little bit before, but just another look at it. So we're trying to draw a function that contains f of 0 equals 4. So at 0, it has a function value of 4. That's pretty cut and dry. That's just a point at 0, 4 on our function. This next set of symbols, this equation, put that into words. What is that telling us we need our graph to have? What do you think, Tristan? At 0, which is kind of the point that I just drew, we need this graph to have a slope of 0. Now, that could look like this. It could be the bottom of a parabola. It could be the top of a parabola. It also could kind of wiggle through it like this, and have a slope of 0 instantaneously right there. There's actually a few different ways to make that happen. So you might want to just hold off on that stipulation until you get some information about what's happening surrounding it. And sometimes it will matter and sometimes it won't. So if we look to our next one, explain to me what this is telling us that our graph needs. Olivia. Okay. When the x is perfect, when the x's are less than 0, so that's over here, the slope has to be negative. There's your derivative having to be less than 0. In other words, there's your slope having to be negative. And your slope has to be negative to the left of 0. So guess what? That gets rid of this option. Because can't we agree that our slope would be positive right here if I went with that graph? So that's out. So I definitely know that coming into that point where the slope will have to be 0, I'm definitely decreasing into it. And then, Mitch, what does this tell me? Right, so my slope has to turn positive once I'm beyond 0. So once I get to the right of 0, my slope has to turn positive, and that really only leaves me with that choice, which accomplishes my slope being 0 at 0. Andrew. Like curve through here. Well, I couldn't just go a straight line and then another straight line, because in that case it would come to a point there. And the derivatives don't exist at points. They wouldn't equal 0. It would be a does not exist if that was the case. But once I get beyond this, once I get through this smooth transition with a negative slope before and I could, do something crazy afterwards if I felt like it. I don't know why you would add in some other kink, but you could. Does that make sense? And so that brings me, let's just capitalize on what he just said. If ever I was told this, if the slope at 0 did not exist, I could do that one in a couple of ways. I could decrease into it, like he said, and then increase out of it, but have it come to a sharp point. That would constitute the slope at 0 not existing. That works? It is? Able to be depositable? It's hard to say. We're going to have to Google that. I'm not sure. So that would be one way. Can anyone think of another way of making that happen? Where it would decrease into 0, increase coming out of 0, and would have a slope that does not exist at 0. Aiden? You want to go draw it? Could you draw it versus explain it? Or no? Well, I'll tell you what, I don't want to put words in your mouth, but when you said radical, I got thinking maybe you meant like something like that. Okay? So that would work. That's very similar. It's decreasing coming in, so a negative slope coming in, and increasing coming out, and still coming to a point. Still coming to a point right at 0. How about something other than coming to a point? Why else might a derivative not exist? Right, you could have an asymptote at 0 in a case like that. You could be decreasing coming into 0, but never actually get to 0, right? But everything up to 0 would be decreasing, and then everything coming out of 0 would be increasing. But again, we can all agree that right at 0, the derivative doesn't exist, namely because the graph doesn't exist. In these other two examples, the derivative doesn't exist even though the function itself does. The derivative does not because it comes to a point. Does that make sense? Okay, so a good little... All right, so I wanted to pull an example from a book, but clearly I didn't want to write it down, probably because there's a diagram involved. So I'm going to jump to page 132, number 54. And, this one. Okay, so take a look at your function. Now, this is not g. This is not a graph of the original function. This is a graph of the derivative of the original function. So, what is g prime of 0? What would you say, Mackenzie? Say it again. -3 is correct. So at 0, on the g prime graph, an x coordinate of 0 gives you a y coordinate of -3. What that tells us is that on the original graph, the slope at 0 is -3. So what would that look like? So on the original graph, at 0, the slope is -3. So when it comes through 0, it's a pretty steep negative. I don't know where it is located, right? It could be way up here or way down here. But on the original graph, the slope at 0 is a -3 slope. Do you see that? Okay. On B, what is g prime of 3? John, are you with me? Okay, what do you think g prime of 3 is? 0. On our g prime graph, an x coordinate of 3 yields 0. So since g prime of 3 is 0, that means on our original g graph, the slope at 3 is 0. Can we wrap our heads around that? So if I go back here, let's pretend I go off of this one. On our original graph, the slope at 3 is 0. So by the time I get to 3, I have to even that out and flatten out the slope. So that on my original graph, the slope at 3 is 0. Does that make sense? Okay? So what can you conclude about the graph of g? Okay, here's another piece of information. Knowing that g prime of 1 is -8/3. What does that mean about the original graph? How could you put that into words, Abby? What does this mean in words? That the slope on our original graph at 1 is -8/3. So again, this is not our original graph. This is just the graph of the derivative that says, essentially contains the point 1 -8/3, which is -2 1/3. So Abby said it perfectly. On the original graph, the slope at 1 is -8/3. So if I went over here and I already have that section of the graph drawn, the slope at 1 is negative 8/3. So like, let me just do this. Negative 8/3 is negative 2 2/3. We said that the slope here was negative 3, and we're saying that the slope here is 0. So it's steepest here, it's mellowing out a little bit, and then it's flattening out completely by the time we reach 3. Does that make sense? And again, this whole section could be shifted up or shifted down. The location of it is not important. It's more of what's happening to the curvature of it based on the slope information we keep getting. Does that make sense? What can you conclude about the graph of g knowing that g prime of negative 4 is 7/3? So in words, what does that mean, Bailey? Okay, so on our original graph, the slope at negative 4, which would be over here, is 7/3. That's a positive number, yes? So by the time I get over here, my graph is actually got to go upwards, yes? So a couple things I could conclude. Either there's a relative maximum where this had to turn around at some point, or maybe there's an asymptote in there somewhere where this is going up and this is going up. But it is increasing, so at some point something funky happened in between. Either we jumped over an asymptote or we turned around, something like that. You could elaborate. It's hard to say yet what exactly happened, but we do know that it went from a positive slope to a negative slope, somewhere in there. Is g of 6 minus g of 4 positive or negative? So let's go to our graph. Well, we actually have to do more on our graph at 6 and 4. So at 4, what does this derivative graph tell us is happening on our original graph at 4? G prime of 4 is what? 2-ish? Can we agree with that? So if g prime of 4 is 2, what does that tell us is happening on our original graph at 4? The slope is 2, so it's still increasing, right? A positive slope means it's increasing. So at 4, we knew at 3 we hit 0. At 4, if it's a positive 2 slope, we know it's actually turned around, right? And can we agree that there's no jumps in slope here? Right? The slope always is existing. This g prime graph is always existing. So the slope is always existing. So it's not like, so that actually answers this question, by the way. We didn't jump over an asymptote. Does that make sense? Because there was never a moment in time where the slope didn't exist. So this just flat out turned around. Okay? Where did it turn around? Well, wherever the slope was 0. So at negative 3-ish, it looks like it turned around. Because at negative 3, it had a slope of 0. So 1, 2, 3. So right there, it eventually had a slope of 0 and turned around. And again, at 4, we have a slope of 2. So it's a positive slope. At 6, because this question asks about 6, what could you tell me about g prime of 6, Nate? You're right. It does not look like it exists. And I'm trying to think, is that just because they forgot to put arrows on the end, or did they intend for the graph to stop? If the slope at 6 doesn't exist, and the slope, it looks like it kind of cuts off at 5, doesn't it? Can we agree with that? Does it look like it stops at 5? Truthfully, I think that that's just laziness on their part. I think it's supposed to have arrows. Let's treat it instead, Nate, like it has arrows on the end. So if you had to guess, what is g prime of 6? Sure. So the slope at 6 is 10. So 1, 2, 3, 4, 5, 6, which means this thing has gotten pretty steep. So there would be g of 6 with a very steep slope, and there's g of 4. What could you tell me about the value now of g of 6 minus g of 4? Is it negative or positive? Positive, because g of 6 is higher than g of 4. So a higher number minus something smaller is a positive. So g of 6 minus g of 4 would be a positive number. Now, that would be a very tough thing to put into words, because we had to guesstimate what our graph looked like based on the fact that the slope was continuously positive, right? So if between 4 and 6 on our derivative graph, not only is the slope positive, which tells us that the original graph keeps increasing, but the size of the positive slope is going up. So the original graph is increasing faster and faster between 4 and 6, going from initially a positive slope of 3 to a positive slope of 10, let's say. So it's definitely in the positives the entire time. Any time that the g prime graph is above the x-axis and in the positives, that means that your original graph is increasing here, because the slope is positive here. And the original graph is also increasing here, because these slopes are positive. It's increasing faster here, because the g prime value is higher, than it is here. But still, both g prime values are in the positive, which tells us our slope of the original is in the positive. And that gets confusing, because the slope of the curve we're looking at is clearly negative, right? But that's because the rate at which our original graph is increasing is slowing down. It's increasing, our original graph is increasing with a slope of 6 here, but it's only increasing with a slope of 2 here. So that's like increasing really fast and then increasing only slowly a little bit later. So that's tricky. That is inevitably going to be a source of confusion, and like you have to really pause and wrap your head around that. And then lastly, is it possible to find g of 2? And the answer to that, like, where is g of 2? So not g prime of 2, but g of 2. Is it possible to find the y value? Not at all. And that comes back to where I said this graph, the only thing we can get on our original graph is the shape. But that whole thing could be shifted up or down. It could be located anywhere. So to be able to know exactly what the y value is for g of 2 is impossible, unless they gave us some indication of location, which they did not. Okie doke? All right, so there. That's why I didn't write that down on your notes. Okay. Flip to the back. Okay. There's a second way of finding the derivative. So the first way is f prime of x equals our limit as h approaches 0 of f of x plus h minus f of x all over h. What that traditional form does is it gives us a general equation that can be used at any x value. So once we find that, and let's say, I don't know, it boils down to 2x plus 7 for a problem, we now can use that formula to find the slope at any x value in the world. Okay? The alternative form of the derivative is specifically used when you know there's one and only one location you care about finding the slope at. Okay? This way we could use the same equation 10 times over to find the slope at 10 different locations on the function. Whereas the alternative form of the derivative only allows us, based on the way it works, to find the slope at a specific value c that we know ahead of time. So let's pretend here's our function, and here's the c value. We know that we are only interested in what the slope is right here. Okay? So what we essentially visually do, which can compare and contrast to what we did there with the difference quotient, is we think of any secondary point. And we don't call it being h units away anymore. We just call it a totally different x coordinate and its y coordinate therefore would be f of x. So CF of C is the location we're looking for the slope, and XF of x is just some other random point, okay? Essentially, rather than what we did before, which was the distance of h between them pinching towards 0, really what we're letting happen is we're letting x slide towards C. So we're looking for the limit as the x coordinate approaches C. And then this is just the slope formula between the two. y2 minus y1, f of x minus f of c, over x2 minus x1, x minus c. Okay? But it's only good to find the slope at a specific value. So take this one for example. They're telling us we want to find the slope of this curve only at 4. So rather than doing this whole thing, since we know the location at which we're looking for the slope, the alternate form can just be much faster. So f prime of 4, the slope of this at 4, we will get by doing the limit as x approaches 4. So that secondary x point is going to slide closer to 4. And f of x is 3 over x minus f of c, which would be f of 4 in this case, is what? What's f of 4? F of 4 equals 3/4 all over x minus 4. We still can't plug in 4 right away to find the limit. We still need some manipulation, but there's less like simplifying out. There's none of those x plus h's to worry about. So we're just going to clear complex fractions by multiplying by 4x over 4x. When I distribute in my numerator, I'm going to get 12 minus 3x over 4x, x minus 4. And again, that limit as x approaches 4 is still out in front. And then factoring and canceling is going to help me out here. I can pull out a 3 from the numerator, and I'm left with a 4 minus x. And then what cancels, sort of, kind of? Mackenzie? Right, so I can cross those out and throw a negative in front. And now I'm just looking for my limit as x approaches 4 for negative 3 over 4x, which now allows me just to plug in 4. And I get negative 3 over 16. So what I find specifically is that on this function, the slope at 4 is negative 3/16. Okay? So again, rather than finding a generic equation and then plugging in 4, we do it right from the start. We're only looking for the derivative at 4, so we can use that alternate form. Okie doke? And then we'll just jump to this one. So we're looking for f prime at 2. So that's going to be the limit as x approaches 2 of f of x, which is x cubed plus 6x, minus f of 2. What's f of 2 here? 2 cubed is 8. 8 plus 12, 20. You go with that? All over x minus 2. So when we simplify the numerator, can we, is that supposed to be a squared? No, I'm nervous. Uh-oh, I might have a typo here that I have to address. If I plug in 2 right away, I'm going to get 8 plus 12. I'm going to get 0 over 0. How do I can't exactly factor that in the traditional method and cancel, but what can I do? How can I divide that out? You could. I'm not thinking most people. Do you know? Do you have any foresight? Is that going to help you? Yeah. You might try it. I don't know that that's going to help you. I'm more thinking long division. Yes? If I do long division, or I can do synthetic here, 1x cubed, 0x squared, 6x, and negative 20. And I can divide out 2 and see what happens. So does x minus 2 go into that evenly? What was my remainder was 0, so it did go in evenly. It started out as an x cubed, and this just dropped down to a 1x squared, a 2x, and a 10. So what I just essentially did by doing long division or synthetic division is I did factor that. X minus 2 was a factor. I had a remainder of 0. And it gets multiplied by x squared plus x plus 10. And so it does reduce. The x minus 2's do cancel. And now I can plug in a 2. And I get 4 plus 2 is 6. 6 plus 10 is 16. So at the end of all that, the slope at 2 was 16. We're going to pick up talking about these tomorrow, but that synthetic division, that kind of digs into our, I don't know, chapter 5 stuff, so it's been a while. There's your homework. We'll see what questions come up, and that's where we'll pick up tomorrow.